Lewis structures. So in order to get to Lewis structures, we need to talk a little bit about electron dot symbols. So electron dot symbols show only the valence electrons. So if we look at fluorine, and if we go back to our periodic table, here, I said that everyone in group 7A has 7 valence electrons. So instead of drawing out all the rings, we can simplify this, and we can just depict the valence electrons. Because in reality, it's only the valence electrons that are going to be reacting in order to form bonds. So, fluorine, 7 valence electrons, and you can draw it out like that. Giving you some other examples, if we wanted to draw magnesium as an electron dot symbol. Magnesium is in group 2A, so it's going to have 2 valence electrons. Potassium is in group 1A, so it's going to have 1 valence electron. Oxygen is in group 6A, so it's going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. I like to do that 4 corners method, going around clockwise. Bromine. Bromine is in group 7A, so bromine, like fluorine, is going to have 7 valence electrons. 2, 3, 4, 5, 6, 7. Lewis structures represent molecules using element symbols and lines for bonds, dots for lone pairs of electrons. So in order to draw a Lewis structure, you first need to determine the number of valence electrons. Then you need to put the valence electrons around the atomic symbol. And then if it's a compound, you're going to continue. So drawing a Lewis structure for any one individual atom is just going to be the electron dot symbol. But if it's a compound, so it's bonded to something, you're then going to determine whether the components are metals or nonmetals, so you can draw the ionic or covalent bond type. If it's a nonmetal, you're going to look up the most common bonding pattern. You're going to draw covalent bonds as lines, each line representing 2 electrons, and ionic bonds with charges including valence electrons on the anion. Examples of covalent bond structures, methane, and ionic bond structures, salt. We're going to go through some examples as we continue through here. So this is just showing you some Lewis dot structures of various atoms. And then, as you recall, I talked about covalent and ionic bonds. So in a covalent bond, there's a sharing of electrons. Because electrons are shared, it's a very strong bond. So covalent bonds, again, I refer to them as a marriage. In a marriage, things are shared. It's a very strong bond. It's very difficult to break apart a covalent bond. An ionic bond, one gives up electrons and the other takes electrons. So ionic bonds I like to refer to as a toxic relationship. So in ionic bonding, one gives everything that they have, the other one takes. And it's not a sharing of electrons, it's one gives, the other is taking. Ionic bonds are weak bonds. A covalent bond, again, consists of a pair of electrons that's shared by 2 atoms of non-metal elements. So when you have non-metal and non-metal coming together, it's a covalent bond. There are some diatomic elements that we discussed earlier, and this is what their Lewis dot structures will look like. I'm going to take fluorine as an example and show you how fluorine forms a bond. So fluorine, let me just add all of this information. Fluorine has 7 valence electrons. So if I draw fluorine and I do 7 valence electrons, now since I'm talking about 2 fluorines bonding together, I'm going to draw another fluorine, and I want to kind of orient the valence electrons near each other, because in order for them to form a relationship, they're going to have to be by each other. So we have 1, 2, 3, 4, 5, 6, 7. Now to depict that these electrons are shared, you draw a line connecting the dots. So we play connect the dots here. And this is how this structure is formed. Now why does oxygen look like this? Well, with oxygen, we have 6 valence electrons. So when I draw oxygen, I'm going to draw 1, 2, 3, 4, 5, 6. And since there's 2 oxygens, I'm going to draw another oxygen, and I want to orient the valence electrons near each other. Because again, in order to form a relationship, they have to be close together. So now I'm going to connect the dots. So these are paired, those are good. But this one can form a bond with this one, and this one can form a bond with this one. So why doesn't this one form a bond with one right here? Well, on an individual oxygen item, we are using the 4 corners method to assign where electrons are positioned. Now these are parents, maybe we're talking about like mom and stepmom or mom and stepdad or whatever, but we've got 2 sets of parents here. Those are not going to separate. They're married, they're good, happy together. And then we have the 2 kids that are going to marry off. So let's say this is brother and sister or sister and sister. Now they can't marry each other because they're within the same family. That would be weird. So they have to form a bond with something from a different family. So that's why we're taking this electron and bonding with something over here instead of bonding with itself in the same family. So that's just another way to think about it, why we are orienting our electrons that way. So now this is really messy, but we can physically see now that 2 bonds would be formed between the oxygens. And now that's why we drew our final Lewis structure like this. Why does nitrogen have 3 bonds? Well, if you think about it, nitrogen is in group 5A, which means that nitrogen has 5 valence electrons. So if we have nitrogen, 1, 2, 3, 4, 5, and another nitrogen bonding together, 1, 2, 3, 4, 5. Again, these ones up here, it's mom and dad, or dad and dad, or mom and mom, whatever. That's the parents. They're bonded together. And these parents have 3 kids that want to be married off. So this one's going to connect the dots with this one's going to connect the dots with that one, and that one's going to connect the dots with that one. This looks terrible, but by playing connect the dots, now you can visibly see that 3 bonds would be formed between these nitrogens. So nitrogen has the 2 valence electrons depicted, the 3 bonds, and the 2 valence electrons, or the electron pairs, sorry, lone electron pairs depicted there. So a table of electronegativity shows how the relative electronegativity of certain atoms. So this is going to be important when we talk about like single displacement reactions and whether atoms would swap out for one another. So we will revisit this, but this is a good reference table to know about. So this periodic table is just here as a reference. Now we're going to try to draw out some Lewis structures based on what we see here. So with this first one, we have CH4. That means we have 1 carbon and 4 hydrogens. Typically, we want to put the most electronegative element in the center. So looking at our table of electronegativity, we want to put the one that's of highest electronegativity in the center. Another thing we can say is that the one with the lowest quantity goes in the center, and all the other ones are going to go around it. So CH4, we're going to put our carbon in the middle. Carbon is a group 4A, so that means it has 4 valence electrons. 2, 3, 4. So we're going to put our hydrogens around it, and hydrogen's in group 1A. And being in group 1A means that hydrogen is going to have 1 valence electron. So we're going to put hydrogen here, and we're going to orient the valence electrons near each other. So hydrogen, and here's hydrogen's valence electron, and here we go for this hydrogen, and this is for this hydrogen. Now that we have drawn all of the electron dot symbols, all we have to do is play connect the dots. So these 2 bond, these 2 bond, these 2 bond, and these 2 bond. And that's our final Lewis structure for methane, or CH4. Now we want to draw CO2. So since there's 1 carbon and 2 oxygen, we're going to put the carbon in the middle. So our carbon goes in the center. Carbon, again, is in group 4A, so it has 4 valence electrons. And now we have 2 oxygens, so we're going to put the oxygens on the outsides. And oxygen is in group 6A, so that means it has 6 valence electrons. I'm going to put the pairs facing on the outside, and I'm going to orient the valence electrons, or the single ones, toward the center, so that they can be oriented by that carbon. So now all we have to do is play connect the dots. So this one is going here, this one is going here, this one to here, this one to here. Now that looks terrible, so we are going to redraw this one, and we're going to put the carbon in the middle, and we're going to put double bond and oxygen, and we're going to keep our pairs on the outside, and we're going to do the same thing over here, and that's our final Lewis structure for CO2. I want you to pause the video and try to draw the next ones. Using the valence electrons and such, I want you to try to draw these out. Okay, so now we have PBr3. So P we're going to put in the middle, and the BRs are going to surround it. So P is in the middle. P is a group 5A. So that means it has 5 valence electrons. 1, 2, 3, 4, 5. Now there's 3 bromines, and each bromine, since bromine is in group 7A, each bromine is going to have 7 valence electrons. So 6 of those are paired up, but there's 1 that can be oriented here. And if we draw bromine down here, again, 6 are going to be paired up, and 1 is by itself here. And we can draw bromine 6 paired up, and 1 is going to be oriented here. And now all we have to do is play connect the dots. We never connect dots to pairs. Those are happy. They're paired up already. And we never want to connect dots from within the same family. We marry outside of our family, because otherwise it's weird. So here we go. Connect the dots, connect the dots, connect the dots. This is our final Lewis structure for PBr3. H2O. So we have oxygen in the middle, and we have 1, 2, 3, 4, 5, 6. We have hydrogen. Hydrogen has 1 because it's a group 1A, and then we play connect the dots. That's our final Lewis structure for H2O. NO minus. So nitrogen bonding to oxygen. We have nitrogen, and nitrogen has 5 valence electrons. And then we have oxygen, and oxygen has 6 valence electrons. And we're going to try to form as many bonds as we can. So we connect the dots here, connect the dots here, and we have 1 left over. Because these are paired, these are paired, these are paired. So when we redraw this, N double bonded to oxygen, we have this one alone. This one's still unhappy. Because it's by itself, it wants to gain another electron in order to be happy. So because it's by itself, we have to depict the presence of this electron. And I usually do that by just doing the charge that we see here and circling it so they know that it's not a bond. So we have a negative charge. That one's left unhappy, left unfulfilled. Now we go NO2 minus. N in the middle, we go 1, 2, 3, because N is a group 5 and it has 5 valence electrons. And now we're going to draw 2 oxygens. So we have 1, 2, 3, 4, 5, 6, and we're going to draw another oxygen, 1, 2, 3, 4, 5, 6. Because oxygen is a group 6A, it has 6 valence electrons. Now we're going to try to connect the dots as much as possible. So here we can connect these two, here we can connect these two, here we can connect that one, but this one is alone. So we can't mess with the pairs, they're already paired up, so this one is kind of left. So in this one we have, sorry, let me start with an O. 1, 2, 3, 4, we got 2 bonds to an N. We have 1 bond to this oxygen, and then we have that single electron that's by itself, and that makes it angry. So we're going to indicate that electron by putting a negative charge on that side. So this would be our final Lewis structure for NO2 minus. Polarity has to do with the electronegativity. If the electronegativity of the atoms bonded together is different, it's a polar compound. Molecules that have double bonds are typically arranged in a straight line and are therefore not polar. But molecules that have a bend are polar. So for example, H2O is polar. If we go back to looking at some of these drawings, this is all even around it. So that's not considered polar. Here, it's in a straight line. CO2 is not considered polar. But here we have some bends where the electronegativity of bromine, if we go to this charge, we look at bromine is more electronegative than phosphorus. So again, the one with the least electronegativity is going to be in the center. The higher electronegativity is going to be around that. So because we have a difference in electronegativity, this is going to be polar. Water. We compare oxygen to hydrogen. Oxygen has a much higher electronegativity, so that means electrons are actually going to be pulled toward the oxygen a little bit. The oxygen is going to kind of have a higher electronegativity. It's going to be pulling the electrons a bit more. Hydrogen is a little bit weaker, so this is definitely polar. So we're going to determine whether these molecules are polar or nonpolar. So if we start with N2, N2 we've drawn previously, so I'm just going to draw it from the example that we gave earlier. We know that N2 has 3 bonds. So it's forming a straight line, and it's even on both sides, so we're going to consider this nonpolar. HF. So H has 1 valence electron, F has 7 valence electrons, and we always want to orient singles near each other when we draw the connection here. And it looks like it's kind of in a straight line. However, if we go back to our table of electronegativity, you can see how much electronegative pole there is on this one compared to this. This is going to be considered to be polar. CH3OH. So we're going to draw the C. We're going to put 3 H's around it. Then we have O next. And we have an H. Now we connect the dots. Connect this, 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 here, and here. So this group and this group are not even. Nothing about this is even, so this is definitely going to be polar. H2S. So S is a group 6A. It's going to have 6 valence electrons. And hydrogen each has 1. So going back to our table of electronegativity, hydrogen versus sulfur, there is a major discrepancy in electronegativity. This would bend, and this is polar. I2, we had this example earlier. I has 7 valence electrons bonded to another I with 7 valence electrons. And then we connect the dots in the middle. This is nonpolar. And then we go to NH3. N has 5 valence electrons. Each H has 1. And then we connect the dots. You might be wondering, how am I putting these dots down where they're supposed to be? And I do want to take a minute to explain this if you haven't followed along to where these dots are going and why I'm putting them where I'm putting them. So if you recall, we want to put the one with the least number in the middle. We always want to orient everything else with higher numbers around that one in the middle. We also want to check our table of electronegativity. So we want to try to orient them such that the nitrogen's going to be in the middle and the hydrogens are going to be around the outside. So with nitrogen in the middle, I drew the electrons in the 4 corners method. So I put 1 electron on the top, then on the right, bottom, left. Then I go back clockwise and I put the last one up on the top. So that means that these 2 up here are full. Now these 3 are available to bond with something else. Each hydrogen is going to have, and I'm just going to redraw this so that you guys can see what I'm talking about. So 1, 2, 3, 4, 5. So these are good. We don't mess with those. These can be bonded. Each hydrogen has 1 valence electron. So it would not make sense for me to put a hydrogen up here. Because this one is not going to break up this pair. So we wouldn't write hydrogen up there. We could put hydrogen here with our valence electron. And we always want the valence electrons facing a potential partner. So when I put my hydrogen down here with its valence electron, I'm not going to write the valence electron here. I'm going to put it here because I want it to face a potential partner. And if I put hydrogen over here, again, I'm not going to put the valence electron here, here, or here. I'm going to put it here so that it can face a potential partner. Now that all of the electrons have been drawn out, all the valence electrons are depicted in the picture. Now I can play connect the dots. I do want to form bonds with something outside of my family. So I'm going to draw this line, and I'm going to draw this line and this line. And that's how I got this final Lewis structure. So now when we look at the electronegativity differences, we can see that this is going to bend and form a polar compound. All right, so that covers covalent bonds. Now we're going to move on to drawing ionic bonds and the ionic Lewis structure. So in the ionic bond, it's a bond that's formed between a metal and nonmetal. Smaller molecules as opposed to large molecules. The metal is going to lose electron and become a positively charged cation, while the nonmetal gains electrons and becomes a negatively charged anion. They're held together because of opposite charges attracting. So one is a giver, one is a taker. They find that attractive about each other, so they kind of hang out. But they're very weak. As soon as a more attractive ion comes along, they will leave who they're with and go with the other one. So it's a very superficial relationship. That point will be important once we get to talking about, again, those single displacement reactions in the future. Believe it or not, there is an attractiveness of elements, and it has to do with an activity series, which we will cover. So assigning charges to ions, you always want to look at the periodic table. Some transition metals are weird, so those ions would be given to you. But here's our periodic table of monoatomic ions. So you can see everyone in group 1A is +1, group 2A is +2, 3A is +3, and then we have -3, -2, -1. So when ions are formed, the metal is going to lose electrons and the nonmetal is going to gain electrons. So we talked about the valence electrons of sodium and how it's very easy for sodium to give up that one electron. Chlorine has 7 valence electrons. It's not very easy to give up 7 electrons, but it is easy to gain or to accept 1 electron. So sodium loses an electron, sodium's the metal. Chlorine gains the electron, and chlorine's the nonmetal. So when we draw out the ionic bond formation, you can see at the bottom the Lewis dot structure for sodium and chlorine. So what happens is instead of playing connect the dots, because we can't do that with an ionic bond, if you remember, you always need to determine whether there's nonmetal interacting or metal and nonmetal interacting. Otherwise, you're going to end up drawing lines where lines do not belong. You never form a line in this type of relationship. So one is going to leave, the other one's going to gain. So you have Na becoming positive by 1 because it just gave up 1 negative charge. Chlorine is going to become negative by 1 because it just gained a negative charge. And this is a picture depicting a sodium crystal. Because one is gaining and one is losing, they have to stay near each other. And they're going to equally distribute in a crystal. So a bond that is principally ionic will form between which atoms? Magnesium and chlorine. So why is it magnesium and chlorine? because one's metal and one's a nonmetal. When you have nonmetals and nonmetals or nonmetals and metalloids, those are going to be covalent. Metal-nonmetal relationships are going to be ionic. The metal is going to lose the electrons, the nonmetal is going to gain the electrons. So the formation of magnesium chloride. One thing I do want to mention, even though we will be spending an entire lecture talking about naming, you can see the name of chlorine has changed to chloride. Chloride means that it's in its ionic form. Chlorine is in its elemental form. So elemental chlorine on the periodic table becomes anionic chloride when it forms ions. Again, we're going to discuss that in more detail later, but I just wanted to point that out since you're now seeing the name on paper. So in order to form magnesium chloride, magnesium needs to lose 2 electrons. Chlorine needs to gain 1 electron. So this is what's actually going to happen. We have magnesium here, and magnesium has 2 electrons. 2 valence electrons. So one of these valence electrons can go to this chlorine, another valence electron can go to this chlorine, and we end up with a final Lewis structure that looks like this. Formation of aluminum oxide. Aluminum has 3 valence electrons. So Al2O3, this electron's going to go to this pair, this one's going to pair with this one's going to pair with this one, and you can see the movement of electrons. And you can see how they end up over here in our final Lewis structure. There are exceptions to the octet rule. Molecules such as SF6 and PCl5 have more than 8 electrons around a central atom in their Lewis structure. These are referred to as expanded octets. Beyond mentioning them, we did not cover those in this class. And if you happen to see this on a homework assignment or on a practice problem, you can just refer back to this slide. But these will not be on a test. So you will not be tricked up on a test using these. So metals generally form ions by doing what? Metals lose electrons, and when you lose negativity, you become more positive. Okay, I'm going to draw out the first 2, and then you're going to pause the video, and you're going to draw out the rest of them, and we will go through them. So the first thing you have to do when it tells you to draw out Lewis structures is you have to determine whether it's an ionic or covalent bonding system. And how you determine that is based on the presence of metals. This first one is sodium. Sodium is a metal, so this is going to be ionic bond. The next one, magnesium. Magnesium is a metal, it's going to be ionic. The next one is calcium. Calcium is a metal, this is ionic. The next one has phosphorus and hydrogen, which are 2 nonmetals. This is going to be covalent. The next one, potassium and fluorine, that is a metal, so it's ionic. Calcium, again, metal. And lithium is a metal. So now that we have determined the metals and nonmetals, and we only have one covalent structure that you'll have to draw, again am going to draw out the first 2, and then you guys will work on the other ones. So we have sodium. Sodium has 1 valence electron. We have iodine, which has 7 valence electrons. We do want to orient the valence electrons so that the ones that are not paired are oriented toward each other. And because it's ionic, we never play connect the dots. 1 is going to be lost, and it's going to be gained by the other side. So our final Lewis structure, we put brackets, the Na, and we close the brackets, and this becomes positive by 1, so we can just put a plus. Then we're going to put brackets, we're going to put our letter I. We do want to draw all 8 in the outer shell because it did gain 1 from sodium, and because it gained 1, we're going to put a minus. Now with this next one, we have Mg, and actually I'm going to let you work on this one. I'm going to do this one because I want you to see how this is going to be depicted. So I have 1 calcium, and calcium has 2 valence electrons. And then I have 2 chlorines, and each chlorine has 7 valence electrons. So this one is going to leave and form a bond with that one. This one's going to leave and form a bond with that one. So I have Ca in brackets that becomes positive by 2. And then I have 2 chlorines in brackets with all of their 8 in their outer shell. And each one of those is minus, because each one of those only gained 1 electron. So this calcium gave up 2 electrons, so it became positive by 2, but each one of these only gained 1 electron, so it became negative by 1. So again, go ahead and pause the video, and then when you come back, I will go through the rest of these answers. Okay. So we have MgO. Mg has 2 valence electrons. And again, how am I knowing this? Mg is a group 2a element. So we have 2 valence electrons, and then O. O is a group 6a, so it has 6 valence electrons. This one is going to form a pair here, and this one is going to form a pair here. So in our final Lewis structure, we're going to have Mg in brackets losing 2 electrons, so that means it becomes positive by 2. And we have oxygen with the full outer shell now because it gained 2 electrons. When you gain negatively charged electrons, you become negative by 2. Going on to this next one. This is covalent. So we're not going to draw brackets. Now we're going to go back to our connect the dots. So we're going to put phosphorus in the middle. Phosphorus is a group 5a, so phosphorus has 5 valence electrons, and we're going to orient those hydrogens around the phosphorus. We're placing our valence electrons so that they're in proximity to another one so that they can share or form that bond. And now all we do is play connect the dots. So we're going to connect this one, and that's our final Lewis structure. Kf, so we have potassium, which has 1 valence electron. We have fluorine that has 7 valence electrons. This one is actually going to leave and form a bond with that one, or form a pair, sorry. So we have potassium in brackets 1 minus, and we have fluorine in brackets with a full outer 8. And this one, sorry, 1 plus over here. And this one, because it gained an electron, it gained a negative charge. This is 1 minus, or simply just minus, like what was depicted above here. In this class, it does not matter if you put 1 plus or just plus. So keep that in mind, but you do always want to put the quantity of the charge first, followed by the symbol. So then we have CaS. Ca, calcium, has 2 valence electrons. S has 6 valence electrons. It's a group 6a. This one's going to form a pair here. This one's going to form a pair here. And we're going to do our brackets. So calcium loses 2 electrons, becoming more positive by 2. Sulfur gains 2 electrons, becoming more negative by 2. That's our final Lewis structure. So then Li3N, we have Li, Li, Li. Each lithium has 1 valence electron. I want to more clearly make those I's and this valence electron. And nitrogen has 3 valence electrons. This one can form a pair here, this one here, and this one here. So what's going to happen is we have Li in brackets 3 times with a 1 plus, or just a plus. And we have an N with its full outer 8 in brackets, and it gained 3 electrons, so it's actually 3 minus. So that would be the final Lewis structure for Li3N. All right, so there's some practice worksheets that you can work through, and then your homework assignment. If you have any questions, please feel free to reach out to me.